So today we will start with new chapter from the new unit, that is unit number 3 and chapter number 8 from your book M. Morris Meno. So unit 3 from your syllabus, we have completed 2 units and 2 chapters from your book M. Morris Meno. Today we are going to start a new unit, that is unit number 3 from your syllabus and chapter number 8. The name of the chapter is CPU, Central Processing Unit, CPU. So most of the students have heard this name before also, right? So why we use
Yes, sir.
Central Processing Unit? The bulk of data processing tasks, all your bulk data processing tasks are done by this central processing unit, right? All your bulk of data processing tasks have been done by this CPU, central processing unit, right? So this is it is also termed as brain. It is also termed as brain of the computer. So first of all, bulk of data processing task. The second one is it is also called as brain of the computer, right? So we have three major components that deals with CPU. We have three major components that deals with the CPU. Those three components are, the very first one is register set. The second component is called as ALU, arithmetic logical unit, and the third component is called CU, that is your control unit, right? And then we have three different categories of buses which have been used with the CPU. The first category is called data bus. The second category is called address bus, and the third one is called control bus, which basically deals with CU. So I am repeating again, we have three major components of CPU. These are the three major components, that is your register set. Register set basically consists of multiple registers which are used for the processing of intermediate data, right? We perform all the data related tasks in registers, right? Then we have control unit. So why we use the control unit? We have already discussed in last chapter. We have studied two categories of control unit. The one is being the hardwired and the another one is being the microprogrammed CU, right? So what is the purpose of using the control unit? These are basically used for the generation of control signals. Remember, these are used for the generation of control signals, right? For those control signals, this control bus will be used, right? So CU issues the control signal to the ALU to perform the specific operation, to perform the specific operation, right? Next we have ALU. ALU stands for arithmetic logical unit. So all your arithmetic operations and all your logical operations, right? We have already done this before in the last chapter. So all your arithmetic operations, additions, subtractions, multiplications, right? They are your arithmetic operations, and logical operations are and, or, NAND, XOR, right? So if you are performing some complements, right? Clear. So all these are your logical operations, right? So all these operations have been performed with the help of ALU, arithmetic logical unit, right? So here we have used three categories of buses. The first category is called data bus, the another category is called address bus, and the last category is called control bus, right? So what is the purpose of data bus? So data bus is basically used for carrying the data. This is used for carrying the data. Address is used for carrying the addresses, where your data or where your operands are stored in the memory, or where you are going to store the result in the memory. That particular address have been fetched, have been given by this address bus, right? Then we have control bus. Now the CU deals with control signals, and control signals are sent with the help of control buses, right? I hope all the three buses have been clear to all of you. I am repeating it again. We have three major components of CPU. The first component is called register set, which is basically store the intermediate data during the execution of its instruction. It is having multiple registers, which is used for the intermediate results. The second component is called CU, control unit, which is responsible for the generation of control signals, right? And how we can generate the control signals? Simply by using the hardwired control or by using the microprogram control. It's up to your choice, right? And the third one is ALU, arithmetic and logical unit. It is basically used for the execution of all the arithmetic operations like addition, subtraction, division, multiplication, etc. And all the logical operations like AND, OR, NOR, XOR, complement, clear, etc. Right? So this. So next we have CPU performs a variety of functions dictated by the type of instructions that are incorporated in the computer. This means that CPU will be performing all the operations which are instructed by the instruction present in the computer, right? So it will perform all the operations given by the instructions present in the computer, right? So in programming, memory locations are needed. All of you are aware about the locations. So you are using the memory locations, right? So in case of programming, memory locations are needed for storing, right? So memory locations are needed for storing the pointers, for counters, for return addresses, for counters, for return addresses, right? Addresses, or temporary result storage. If you want to store your result, even though you will require memory locations, etc., right? So memory access is most time consuming, right? You are aware about that. Memory, if you want to access some location, it is much more time consuming. So what is the alternative way? If you don't want to access your memory, what is the easiest way? What is the fastest way, right? So we are using the concept of registers instead of memory, right? So instead of accessing the memory, we are going to store our data inside the registers. so that to decrease the access of memory location, because the data is fetched more faster rate in case of registers as compared to memory access, right? So registers are faster as compared to memory. They what is the reason of being the faster? Because they are large in numbers. We have large registers and they are small in size, right? So I hope the concept is clear to all of you, right? So I'm repeating it again. In programming, we are constantly accessing memory locations. Why we are accessing memory locations? For storage, to store the results or to fetch some data from the memory. The second one is for counters, for return addresses. If you want to return your address, again you need memory location, and for the storage of temporary storage of results, right? So these are the four reasons why we use the concept of memory locations, and this is the reason why you don't prefer memory, right? So because the data storage in case of registers are much more faster as compared to the access in memory, right? So next we have CPU is CPU is governed by its organization. CPU is governed by its number one organization, number two instruction set, number two instruction set, number three addressing modes, or you can say that instruction formats, right? So you can govern the CPU by any one of the category. Number one, by its organization, instruction set, addressing modes, or instruction format, right? So the main function of the CPU is to fetch the instruction from the memory and to execute it. What is the main function of CPU? Simply to fetch the instruction. Suppose this is your memory. This is your memory. Now the CPU's function is to fetch to fetch the instruction from the memory and to execute that particular instruction. So this is the simple function of your CPU, right? So we have discussed one more function. All the bulk of data processing tasks have been performed by the CPU, right? So according to the organization, so we have governed CPU with the help of these four categories. Now, according to the organization, the CPU is further categorized into three parts, right? According to the organization of CPU, the CPU is further bifurcated into three parts. Number one, single accumulator organization. Number one is called single accumulator based organization. Number two is general register based organization. Number two is general register based organization. Last but not the least, which is very important, which is called stack based organization, right? So I am repeating it again. CPU is divided into three categories according to its organization. The very first category is called single accumulator based organization. In this organization, your one of the operand will be present in accumulator always. Suppose you are performing addition operation and you are using this single accumulator based organization, your one of the data values will be residing in the accumulator and the second value will be in register or in memory, right? Suppose, let me give you the example. I will give you the overview of these two only because these two are not in your syllabus. We have stack based organization in our syllabus, right? So I will give you the small overview about these two, right? And we will be discussing in detail about stack based organization, right? So let me clear this point to all of you. Single AC based organization. Suppose if you want to perform add B, right? Add B means that your one of the operand will be in accumulator and the another one will be in register. So according to this instruction, add B, this means that the contents of register B, let's suppose its value is 100 and the value of accumulator is 200. The contents of register B is 100 and the contents of accumulator is 200. Now, what will be the result? The accumulator's value, that is 200, it will be added with the value of register B and the result storage will be done in accumulator itself, right? That is why this is called single AC based, single accumulator based, right? So your second example can be of the form of add M 200. Now what does this instruction will do? It will add the contents of memory location given by 200 location. Now your contents will be present at 200 memory location. 200 is not your data, right? 200 is not your data, but you will find your contents at 200 location. This is the memory location where you will find the data. So in this case, what will be the result? Again, the contents of accumulator will be added with the contents of memory location and the contents of accumulator is 200 and the contents of M of 200 is 150. The result will be 350 which will be stored in the accumulator, right? So again you can find that your one of the operand, your one of the data value will be present in accumulator, right? So that is why this instruction, this organization is called single accumulator based, right? So next, the second category is called register based organization. I'm just giving you the overview of these two organizations because they are not in your syllabus. So second one is called register based organization, right? So in register based organization, the one of the operand will be residing in register and the another value will be fetched from the memory, or it will be done through register to register transfer, right? It will be done through register right? So for example, if I am saying that load R1 comma R2, so here you can see that in instruction both the data values will be in registers, right? So we have, this is your source register and this R1 is acting as your destination. So data movement will be from, very good, right? So your result will be stored in this sequence. The contents of R2 will be copied in R1 and the previous contents of R1 will be washed away, or you can say that overwritten, right? So this is the first example, or we can take one more example, that is you can also write it as add R1. Second one is add R1 comma B. So what it will do, it will add the contents here. B will be acting as in two forms, either it will be your memory location, how, that is M of B, or it will be your register. B will be your memory location, that is M of B, right? And it will be your B simply register, right? So again, add R1 comma B, the contents of register B will be added with the contents of register R, and the result storage will be done in register R1, right? So this will be the result of this particular instruction, that is B, if B is a register, right? If B is your memory location, then you need to write M before B. So here you can easily see that your one of the operands will be residing in registers, or both will be in registers, right? So let me proceed with the third organization, which is in your syllabus, that is, very good, stack based organization. So have you heard this term stack before?
Yes, sir.
Stack based ORG, that is stack based organization. So what does stack means? So for example, we have some stack of books, we have some stack of coins, we have some stack of plates, right? So let me understand one concept. Give me some notebooks. Give me 2 to 3 notebooks. So first of all, stack works on the principle of last in, first out. Remember this. Stack works on the principle of last in, first out. So let me show you the practical implementation. Let's suppose I have one notebook in my hand. So this book is placed at the very first position, right? After that, the second notebook is, I'm going to place the second notebook, right? Now the turn for the third notebook. Now you can see that this one is the last in, but it will be the first out. This third notebook will be placed at the last position, but it will be taken out at the very first position, right? You can't take the middle one, or you can't take the last one. If your stack is very large, it will be very difficult, right? So again, very important point to note. Now the concept is you can use only one end, and that end is called TOS. That is, this end is called TOS, that is top of the stack, and the pointer which deals with TOS is called stack pointer, SP, right? So let's suppose this pen is the pointer. Now it always deals with the top of the stack. So initially it will point to the first book when above two books are not inserted, right? So it is pointing to the very bottom book. After that, when the second notebook has been inserted, it will point to that book. When the third notebook has been inserted into the stack, then the pointer will point to the top of the stack, that is your last book, right? So this thing is called last in first out, right? This thing you have heard it before. So I am introducing one more new thing you haven't heard it before, that is fee low, first in last out. So what is your, which is your last, the very first book notebook is which is present at the last position, and according to that, first in that book has been placed at the very first position, so it will be taken out. So I am taking the first book, then the second book, and this is your last book. So it has been pushed onto the stack at the very first position, but it will be taking lastly. So you can also call your LIFO as philo, right? So LIFO or philo is the same concept, right? One more, thank you very much. One more thing is there, that is FIFO, but don't confuse it because this is your first in, first out. This is your simply a queue. We are not discussing about FIFO, right? We are discussing about LIFO or philo. So all the abbreviations are clear to you. I have written a total 4 things on the board. I hope all the things are clear to everyone.
Yes, sir.
Yes, sir.
Good. So stack is a storage mechanism such that the data items are stored in consecutive locations. What does this mean? The memory is your stack memory is of the form of this. Here your data items, let's suppose D note is the first data item, D note, then we have D1, then you have D2, then you have D3. So these are your consecutive memory locations. So stack is a storage mechanism in which your data items written with the help of D note, D1, D2, D3, it will be stored in consecutive memory locations, right? So their data items are accessed by the mechanism. These data items will be accessed by the mechanism last in, first out. So stack is the concept, as I have already given you the example of stack of notebooks or stack of plates, right? So which are placed one over the another. Any new plate or any new notebook is to be added at the top of the plates, right? So again, if you have to remove any data item, let's suppose if I have to remove this D3, again it will be removed from the top. So remember this point, TOS will be dealing. So you have only one end. You have only one end, which is called top of the stack, right? So you can use the stack as the number of registers or part of your main memory, right? So your stack memory will be organized into two forms. The first one is called in the form of registers, and the second one is called the part of your main memory, right? So next the concept is why we use the concept of stack. What is the need of stack? So your intermediate data generated by the computer cannot be accommodated in registered. Sometimes what happens, you have bulk of intermediate data which have been generated by the computer. So that intermediate data sometimes cannot be stored in the registers, right? Because registers are varied according to the architecture. If you are using 8085, you have 6 to 8 registers. If you are using 8086, register set varies. If you are using i3, if you are using i5, if you are using i7, your register set will vary, right? So we have bulk of intermediate data. So your registers are not enough to store this data. So your part of memory will be used as stack, right? Because the registers are very limited in numbers, hence there must be some mechanism so that bulk of intermediate data can be stored and can be retrieved easily. You are doing two things. The first thing is you are storing the data into the register, and again later on you have to use that data for your later processing, right? So instead of this registers, we have chosen the concept of stack implementation. So this is the first advantage of using the stack organization, right? Now, the second advantage is stack implementation is always there in the computer for multi-programming concept, right? The second advantage of using the stack is it will help you for achieving the multi-programming concept. So next category we have two basic operations. We have two basic operations which have been performed using stack. The first operation is called PUSH, push operation. The second operation is called as pop operation, right? So I'm repeating it again. Push and pop operation. So push means you are simply inserting something, you are adding something. It simply means addition of new data item. That thing is called push operation. And pop means deletion, deletion of the already existing item from the stack, right? So push means addition and pop means deletion. So I already told you that SP is a pointer whose full form is stack pointer, which will be always pointing to your TOS, top of the stack, right? So let me show you how this push operation is performed, right? So one more register which deals with the data, that is data register, DR, right? So let me clear you how this push operation will be performed, how the new data item have been inserted, right? So first of all, the process of inserting a new data item into the stack is termed as push operation, that is performed by first incrementing the stack pointer to the new location. Let's suppose here you have some data items written with denote, d1 and d2. Now this memory location is empty. So first of all, you need to increment. So where your stack pointer is pointing, your stack pointer is pointing to this position. So I will mark it as SP, right? So first of all, what you have to do, if you want to perform the push operation, you will have to increment the value of SP by 1. That is, SP goes to SP plus 1, right? Now you will have to move your data item which is present in the data register, right? So your value which is present in the data register, it will be moved to the M of SP. So here if I give it counting 0, 1, 2, this is 3. So what will be the new value of SP? That is 2 plus 1. It will be 2 plus 1. The new value in SP is 3. So here M of 3. So the value of dr is, let's suppose, d3, right? So M of 3, the new value is d3. So now d3 will be stored at M of 3 and your pointer will be moving towards this location, right? So this is your push operation, right? So this is regarding the operation. Now we have some conditions which needs to be checked before the insertion of a new data item. What is that condition in case of push? So that condition is called overflow, right? Which condition you need to check in case of push? That condition is called overflow. What does this means? That you need to check that whether there is some empty locations present in stack so that a new data item has been inserted. If your stack is already filled, that condition is called overflow, right? Suppose you have a bucket full of water. Now, can you insert some more water into the full bucket? No. What will happen? Overflow. Overflow of water will be taking place, right? So that condition is called overflow. So it needs to be checked before the insertion of new data item into the stack organization, right? So before inserting a new data item, it should be checked that whether a stack could accommodate new data item, full stop. So overflow is the condition resulted when we try to push data item in the stack which is already completely filled, right? You are inserting something, but there is no empty position. So this stack is already filled. Now, can you insert something into this stack? No. You will face one condition which is called overflow. So before the addition of new data value, you have to check the overflow condition, right? So next we have the second operation, that is push pop pop. So pop means deletion. So how it will be performed? So first of all, now what you are going to do, you are removing this D3 which is present at third location, right? So first of all, you have to write M of SP. M of SP is 3. Now you have to store the M of SP into the data register first. After that, your stack pointer will be decremented, right? If you remove this D3, what will happen? Your stack pointer will be pointing to this D2, right? So first of all, M of SP, the contents of M of SP will be sent to data register, and then the value of stack pointer will be decremented by 1, right? So this thing is called pop or deletion, right? So we have used two methods, push and pop, and I have applied the concept of stack by increasing the memory addresses. Here you can see that your addresses are 0, 1, 2. That is, addresses are increasing, right? You can also implement this stack using decreasing memory addresses. We will discuss it in few minutes, right? So let me clear the condition in case of pop. If some condition is happening in case of push, and it is easily understandable that one more condition which will be happening in case of pop, and that condition is called underflow. Very good. That condition is called underflow. Underflow means that now you are deleting something from your stack, and from the already deleted, your stack is already empty. Now you are trying to delete something. So can you delete it? No, never. That condition is called underflow, right? So before accessing the data item from the stack, it should be checked that stack should not be empty. So underflow is the condition when we try to delete or when we try to pop data item from the empty stack, right? So these two examples which we have discussed, they are the implementation of stack by increasing the memory addresses, right? So under this, we have discussed the increase order of memory location. So let me take one more example, which will show you the stack implementation in decreasing order, right? So now you have the stack and you have the SP pointer, that is SP. In this case, the values are like 6, 5, 4, 3, 2, 1. So what is this? Decreasing order. In previous example, we did increasing order, that is 0, 1, 2, and so on, right? So D0, D1, D2, D3, and this is your stack pointer, right? And your data register. Now, what will happen in case of push operation? Now, in this case, what you have to do? First of all, your counter will be decrement because you have to move one position above. So first of all, the value of SP will be decremented. In case of increasing memory addresses, it is incremented, right? Clear? So after that, the contents of dr the contents of dr will be moved to m of sp. So this is your decreasing memory address, decreasing memory address, right? So this will happen in case of push. And if you are performing pop operation, if you are performing pop, so let's suppose by pushing this new d2 value is written and your pointer is at this location after this push operation. So now you are going to perform pop operation. So first of all, the data item will be given to dr this d2. Its location is m of sp, that is m of sp will be given to dr. After that, this value d2 will be given to this data register and the contents of value stack pointer will be very good. Your sp will be incremented by 1 because you have to shift to below position and it is increasing. So this is the case in case of decreasing memory addresses, right? So we have discussed both the implementations of stack in case of increasing memory addresses and in case of decreasing memory addresses, right? So, so next concept is addressing modes. So the term addressing mode refers to the mechanism for specifying operands, for specifying the operands. How you are going to use the operands, how your operands are fetched, that thing is termed as addressing modes, right? So we have in instruction, we have op code, that is your operation code, and we have operand. How this operand will be used in the instruction, right? So whether it is your data, whether your data is operand, secondly whether it is the address of cpu register, or it is the memory location, right? So an operand may be specified as the part of the instruction. First of all, it is the part of your instruction. This complete thing is your instruction. If you remember that we have written this thing earlier, 0 to 11, 12, 13 and 14 is acting as your operation code, and this is the bit number 15. Remember, and this complete is your 16-bit instruction, right? So I am talking about this part, 0 to 11 bits, which will be any of these three things, right? So an operand may be specified as the part of the instruction, or the reference of memory location can be given, right? So an operand could also be an address of the CPU register, right? So first of all, the definition: the operand of an instruction is stored in main memory or CPU registers. So what this addressing mode means, different methods are used for specifying the operand in an instruction. I'm repeating it again. Different methods are used for specifying the operand in an instruction are called addressing modes. What is the definition of addressing modes? Different methods, different methods are used for specifying the operand in an instruction are called as addressing modes, right? So a computer may use one or more addressing modes depending upon its organization, right? So a computer may use one or more addressing modes depending on the organization. So this is the definition. Next we have why we need addressing modes. What is the need of addressing mode? The first one is efficiency. Efficiency in terms of time or space. Time means how much time a particular instruction will be taking for its execution. That is called efficiency in case of time, in terms of time, right? And how much space, how much memory it is consuming, right? After the execution of that instruction, that thing is called space, right? Time means how much time it is taking, and space means how much memory it is consuming, right? The second one is called economy. Economy means whether they are cheaper or not. That thing is called economic. You have listened the term economic. This solution is very much economic one. That is pocket friendly solution, right? That thing is called economy. And the third one is called programming flexibility. So if you are using the concept of addressing mode, you are giving programming flexibility, right? So these are the three different needs with the help of which we are using the addressing mode, right? So let me start with the uh, listen this thing. These addressing modes are helpful. These addressing modes which we are going to discuss in 2 to 3 minutes, right? These different addressing modes are helpful in writing small, efficient and fast programs. These modes are handling complex data like indexing of an array, comma, looping, comma, program relocation and pointer to memory. I'm repeating it again. These different addressing modes are helpful in writing small. First one is in writing small, comma, efficient and fast programs. These modes are handling complex data like number one, indexing of array. Number 2, concept of looping. Number 3, program relocation. And number 4, pointers to memory. Pointer to memory, right? So let me start with the types of addressing modes, right? So next topic is various types of addressing modes. So we have 10 types of addressing modes. These addressing modes are very, very important from the examination point of view. So we will be discussing all these 10 types. So the first type is called immediate addressing mode. The first type is called immediate addressing mode. So what does this immediate the operand is mentioned explicitly in the instruction. Immediate means the operand is mentioned explicitly in the instruction. Operand is given explicitly explicitly in the instruction itself, right? So the instruction is having operand field rather than the address field, right? The basic syntax is opcode and the operand. So here you have the operand field rather than the address field, right? Hence, no fetch operation is required. When you need the fetch operation, when you have some memory. So here, no fetch, no fetch will be required because you don't have the address field. You don't have any address, right? So this mode provides data to its operation code immediately. Why immediately? Because your data is present in the instruction itself. That is why this is called immediate addressing mode, right? So the syntax is written on the board. Let me write the example. So the first example is add R1, 15. Add R1, 15. So you can see that the value, the data is present in the instruction. The data is given immediately. That is why this is called immediate addressing mode, right? So what it will do, the contents of register R1, let's suppose the value is 50. So the contents of register R1 will be added up with the immediate data value, and the result will be stored into the R1. So here you are having 65 as an answer in the R1 register, right? So the second example, this example is clear. The second example is move R naught, 300. So again, you can see that 300 is the data value which will be moved to the R naught register. after the execution, right? And in some assembly languages, it will be written move r note comma hash 300. So both are the correct syntaxes, right? In some books or in some languages, assembly languages, a hash sign is inserted before the data value, right? So disadvantage, the value of data is limited by the length of operand field in the instruction. So this is the disadvantage, right? What is the disadvantage? So this is your operation code and this is your operand. If you have 8 bits of instruction, if you have 8 bit of instruction, this length will be restricted to, according to this 8 bit, you have to give some bits to operation code, and out of those bits, some bits will be used for this. If you remember 16-bit instruction, we have given 3 bits to operation code and 0 to 11, that is 12 bits have been given to operand or your memory addresses, right? So this value will be dependent upon the size of your instruction, right? So this is one is the limitation, that is the value of data, this value. So here operand is acting as your data, right? So the value of data is limited by the length of the operand field in the instruction. Next, advantages. So what is the advantage? Here you don't need to refer the memory. You don't need to refer the memory. The data is present in the instruction. So the advantage is no additional memory fetch access are required for fetching the operand, right? So the second advantage is if you don't refer the memory, it means it is very fast, right? It is very right. So if you don't refer the memory, you don't wasting the time accessing the memory, so it is fast, right? So the second one is, the second is implied or implicit. This one is called immediate addressing or explicit addressing mode. You can call this as immediate or explicit. Explicit, sorry. Now the second category is called implicit or implied. Implied or implicit, or the third name is called inherent. Inherent addressing mode. So in this mode, the operands are specified implicitly. The operands are specified implicitly in the definition of instruction, which means that you will get the definition according to the instruction itself, right? You don't require any operand. So this means operands are not present in the instruction. So its syntax is only this. There is no operand. This is the syntax. You have only operation code, right? So for example, first example is pop. Pop means you are deleting something. The second example is STC. STC means you are setting the carry flag. The next example is HLT. You are halting, you are stopping the processing. The next example is CMP. CMP means you are complementing accumulator, right? You can also write it as this. CMA means complement accumulator. Or next, you can write it as CIR, CIL, or INC. So from these instructions, you can easily judge that these instructions are performing these sort of operations. So you don't find any operand over here. I haven't attached any operand, any operand, any operand. So all these instructions will belong to the category of implied or implicit or inherent addressing modes, right? So this is done for today.